back. So today we're going to do a really quick video on alloys. So we've been dealing primarily with single crystal, single crystal, perfect crystals. We're finally getting into defects, but oftentimes in our SRD lab we've worked with copper, we've worked with chromium, but lots of times we're going to be working with alloys. So alloys are when we form, basically, are when we mix. It doesn't have to be metals. It could just be we're mixing one or more or two or more species to form some type of solid or liquid solution or solid solution, or essentially whatever. Whenever we're mixing two different types of materials, so that's kind of the key aspect of an alloy. So brass. So brass is made of copper and zinc. Titanium 6-4, titanium 6 aluminum, 4 vanadium. And there's actually lots of other elements as well. But you can see that this is an alloy composed of titanium, aluminum, vanadium. Stainless steel has basically stainless steel is going to have iron, chromium, probably sometimes nickel, etc., etc., etc. When you're working with alloys, the major component is going to be called solvent, and the minor component is going to be called the solute. So that's typically, again, how you're going to work with alloys. So here for titanium 6 aluminum 4 vanadium, this is going to be the solvent, this is going to be the solute, just like back in chemistry. And then it could be this interstitial solid solution. Substitutional, again, depending on where it goes. So sometimes when you're mixing, for example, when you're making steel, I'm just going to probably some carbon as well. If I'm doing steel, it's going to be composed of iron and carbon. In this lattice, so iron, if it's in BCC or FCC, let's say it's BCC, the copper atoms are going to kind of exist, again, in these kind of interstitial sites. But some, like copper, zinc, you could have, again, them occupying basically where the copper should be, so the substitutional solid solution. Some general rules for when you're forming an alloy. The atomic radii should have these differences of plus or minus 15%. Ideally, you'd have the same crystal structure, again, so that those there's not basically this kind of meshing or these kind of, basically, if you kind of think of, you have like this BCC like interface where you have BCC on the interface and then FCC on the other interface. That's not energetically favorable. So ideally, you want them to have the same crystal structure. And again, the maximum allowable concentrations of interstitial impurities is really less than 10%. This is going to be very, very important when we get into lecture 7. So you can't kind of indefinitely just increase, you can't just increase carbon forever and make that steel more and more and more and more strong. So that's kind of the idea there. Also, when we get to phase diagrams, you could kind of do a weight percent. You could do an atomic percent as well. And we'll kind of, you could kind of just remember those hopefully from chemistry and those definitions. So that is alloys. So in the next video, we are going to get into point defects, Kroger-Vink notation, Schottky and Frankel defects, and that's going to be a fun video. So I'll see you all in the next one. Thanks. Bye.